All right, now we're going to talk about independence and independent and identically distributed random variables. Um, so lots of things are independent, but they still have the same distribution. So what do I mean by that? Two random people from the same population each flip the same coin. So if I'm looking at the distribution of that random variable, if I draw these two people, they're both being drawn from the same population. So if I say, what's my best guess as to whether this person flipped heads or tails, it's 50-50. What about for that person? Also 50-50. So they have the same distribution, but it's also reasonable to assume that what one person flips for their coin has nothing to do with what the other person flips. So they're independent in this case, but they have the same distribution. Okay, so generally speaking, things that are IID, or we'll see the most common use case for IID is saying, like, if I have a measurement taken on a particular person, two different people from the same population, we will assume that those two measurements are IID, independent and identically distributed. But that's not always the case. So that's what we're here to talk about. So the definition, X and Y are IID if and only if these two things hold. So we need both X and Y being independent. We also need that the marginal density of X is equal to the marginal density of Y. They have the same distribution function. Okay. So if both of those are the case, then X and Y are IID. And what are the points here, right? So I'm drawing a Venn diagram, but what are the points? Well, the points are these joint distributions of X and Y. So there are some joint distributions that you can come up with where X and Y are independent, for example, where they factor, right? And there are some joint distributions where you can come up with where the marginal densities are the same, but they're not independent. But all the marginal distributions that you can come up with between X and Y where they are independent and they have the same marginal distribution, that's IID. So notationally, we usually write X, Y, IID from some distribution, so normal, uniform, whatever, to say that these two things are independent, but they have this shared distribution, or it's not shared, but they both happen to have the same distribution. So for example, normal, and again, because normally this is used for to describe the same measurement taken on different people in the population. So the most common use that you will see of this is notation like this. So x1, x2, ... xn. So where these are the measurements taken on n people in our sample of data, you'll say that those things are IID from some distribution. Some distribution D, something like that, okay? So that's the most common case that you will see. So now our question is, are these following measurements plausibly independent, identically distributed, or both? So again, this is just conceptual. So the first example is where we take two random Berkeley students and measure whether they have the flu. For this one, they're being drawn from the same population of Berkeley students. So I would say that they have these two measurements have the same distribution, because if I take one person at random and say, do they have the flu? And I take another person at random and say, do they have the flu? I get the same chance of somebody having the flu, right? It doesn't matter who I take. But they may not actually be independent. And the reason is that if I take one person and I see that they have the flu, I actually I can do better at guessing whether another random person is going to have the flu. Why? Because these two people are are both Berkeley students, right? Flu is a contagious disease. So if I see that somebody has the flu, maybe that tells me that there could be an outbreak going on. And therefore, it's more likely if I draw another person that they will also have the flu. So this is the kind of one of the canonical examples of when variables, the same measurement taken across multiple people in a population may not be independent. In terms of public health, that's very often not going to be the case when you're talking about measurements of things that are contagious or things that have social network effects where different people are talking to each other and influencing each other. So that's just something to be aware of. So here's another example, which is very similar, but now I've said that we have a Berkeley student and an Oxford student. And now, because a reasonable thing to assume is that these populations are so different, the level of contagion at a given time in Berkeley is not representative of what's going on in the UK. So I would say that they're plausibly independent, right? Knowing that somebody at Berkeley has the flu doesn't necessarily tell me what the kind of outbreak status is in London or around that area. So they're plausibly independent. However, now they may not be identically distributed, right? Because the kind of baseline level of flu in Berkeley and the baseline level of flu in Oxford may be different. So those two things don't necessarily have the same distribution. And now the last example, 2 random Berkeley students, and I measure whether or not they're born in California. So here there's no kind of social network or contagion effect, so it seems pretty reasonable to assume that they are indeed independent, and we already established that they have that in this kind of case, since they're drawn from the same population, they have the same distribution. So to summarize this, I think here it's reasonable to say that we have, let's just say like independent, and then identically distributed. So you can just make a little table. Here, these are not independent. They are identically distributed. Here, they plausibly are independent, not identically distributed. And here, plausibly both. Okay. Hopefully that helps clarify those ideas. So independence among different people in a population is a very common assumption. For the purposes of this course, we will assume that is the case. So that does certainly rule out studying things where contagion, for example, is super common, or where there's social network effects. But the vast majority of statistical methods that you will see applied in public health do assume independence between observations. Now, of course, there's a huge amount of work and courses and things that you can take to study the case where that assumption is not made. That is better studied once you've understood how things work with independence, because it's more complicated to study, much more complicated to study cases where things are not independent. And you end up, so if you've heard of things like random or mixed effects models, that's often used to study that situation. It often requires making a lot more assumptions, because if you can't assume that things are independent, you need to assume some other kind of structure in order to make progress. So, for example, you have to assume, well, one person's disease status only depends on some small number of other people's disease status and not on everyone else's in the population. And it gets quite complicated and mathematically tricky to do things. So I'm not going to talk about that in this course, not because it's not important. It's very important, but because pedagogically, it's not a good idea to start thinking about those things until you've really understood the fundamentals.